want to take the derivative of the hyperbolic trig function. So let's get started with the hyperbolic sine here. So the derivative here, well, y prime, or however you want to write it here, derivative of the hyperbolic sine of x with respect to x is equal to, well, I'm just going to do it in terms of these exponentials here. Well, the times a half comes along for the ride here, right? Because it's just a constant times the function. Excuse me. And then I have the derivative of this difference, so I need the derivative of the first part. The derivative of e to the x is e to the x, and then minus the derivative of e to the minus x. Well, the derivative of e to the minus x, that's an e to the u, so it's an e to the u still. Don't change the exponent, but then multiply by the derivative of that exponent. So then I multiply by negative 1, which makes that a plus 1. And look at that. E to the x plus e to the minus x over 2. That I recognize as being the hyperbolic cosine. So the derivative of the hyperbolic sine of x is the hyperbolic cosine of x. Wow, that's cool. I mean, that's very much like regular trig functions. Okay, but now we got hyperbolic trig functions. All right, now let's move on to y equals the hyperbolic cosine of x. I bet you got a guess as to what its derivative is. I wonder if you're right. I'm going to write this as e to the x plus e to the minus x over 2. And so now let's take the derivative. Y prime is the derivative of the hyperbolic cosine of x. And again, the half comes along for the ride, and then I'm taking the derivative of e to the x plus e to the minus x. So that's e to the x plus e to the minus x times minus 1. So we end up with an e to the x minus e to the minus x over 2. This is equal to the hyperbolic sine. This is even better than the trig functions. The derivative of the hyperbolic sine is the hyperbolic cosine, and the derivative of the hyperbolic cosine of x is the hyperbolic sine of x. Right? No minus sign in there. That's just lovely. So actually, if you took the second derivative of the hyperbolic sine, you get back to itself. You take the second derivative of the hyperbolic cosine, you get back to itself. For regular sine and cosine, it takes 4 derivatives to get back to where you started. But here, it just takes 2. Actually, an e to the x just takes 1, doesn't it? Anyway, that's those. How about the hyperbolic tangent now? So if I look at y equals the hyperbolic tangent of x. Now this one I'm not going to go back to the exponentials. I'm going to think of this as the hyperbolic sine divided by the hyperbolic cosine, both of x, right? Hyperbolic cosine of x. And use a quotient rule. So to take the derivative now, the derivative of the hyperbolic tangent with respect to x is quotient rule. Whatever was on the bottom, I've got it squared, so I've got a cos squared x on the bottom. I've got a cos x times the derivative of the top. Well, the derivative of the top we just figured out is also cos x, minus the top, which is sinh x, times the derivative of the bottom. Well, the derivative of cos x is sinh x. So what I end up with is cos squared x minus sinh squared x all over cos squared x. And that numerator is lovely because remember, cos squared x minus sinh squared x is 1. For regular trig functions, you need a plus sign. For hyperbolic trig functions, there's a minus sign in between. So this is 1 over the cos squared x, which is the hyperbolic secant squared of x. So the derivative of the hyperbolic tangent is the hyperbolic secant squared. That's very similar to your regular trig functions. Just hyperbolic trig functions now. What time do we have? Lots of time. So let's keep going. How about y equals the hyperbolic cotangent of x? Let's write that as the hyperbolic cosine divided by the hyperbolic sine and see what happens. So the derivative now, derivative of the the hyperbolic cotangent, is quotient rule. I've got a sinh squared x on the bottom. I've got a sinh x times the derivative of the numerator. The derivative of the numerator is also sinh x minus the numerator times the derivative of the denominator, but the derivative of the denominator is cos x. And what I have is a sinh squared x minus cos squared x over sinh squared x. And what happens? Cos squared x minus sinh squared x is 1. So if you have it the other way around, that's actually equal to minus 1. So there's a minus 1 on the top. It's a sinh squared x on the bottom for a grand total of negative cosec squared x, the hyperbolic cosecant. Right? So that's a little different because of the minus sign. Or is it? Maybe there was a minus sign for regulars as well. So we've done the sine, the cosine, the hyperbolic, cotangent, tangent. We must be ready to do the secant. Here we go. I'm just kind of hustling through these things. You can rewind and watch them again if you need to. So now I'm going to look at y equals the hyperbolic secant. I'm going to think of this as 1 over the hyperbolic cosine and use a, actually, what I'm going to do is I'm going to think of it instead like this. I'm going to think of it as just a hyperbolic cosine x to the negative 1 power. It's not inverse, right? It's just, it's the reciprocal. So it's thing to the minus 1 power. So when I take the derivative, I'm going to use a chain rule here because this is minus 1 times the hyperbolic cosine of x to the negative 2 power times the derivative of the inside, which is just the hyperbolic sine. So I end up with the negative hyperbolic sine x divided by the hyperbolic cosine squared, which I could write this way as minus 1 over the hyperbolic cosine of x times sine x, hyperbolic sine x, over the hyperbolic cosine of x. I mean, I could have left it like that, but generally it's written this way, as minus the hyperbolic cosecant, no, that's hyperbolic secant, times the hyperbolic tangent. A little bit different because for regular trig, the derivative of the secant is just secant x times tangent x, but now it's minus because of the hyperbolicness here. And one last one before we're done here. I've got y equal the hyperbolic cosecant, which I think of as the reciprocal of the hyperbolic sine. So not the inverse, but the reciprocal. Right? And I'm putting the minus 1 here. I'm saying that thing to the minus 1 power. So the reciprocal. So the derivative now of the hyperbolic cosecant is minus 1 times this thing to the minus 2, where that's a hyperbolic sine on the inside, but then multiplied by the derivative of the inside, which is the hyperbolic cosine. So I end up with minus the hyperbolic cosine of x on top and a hyperbolic sine squared on the bottom. And again, I'm probably not going to leave it like that. I'm going to write it as 1 over the hyperbolic sine of x times the hyperbolic cosine of x over the hyperbolic sine, for a grand total of negative the hyperbolic cosecant times the hyperbolic cotangent. Okay. The derivatives are very similar. Personally, I have trouble remembering the plus and the minus signs, so I derive them. If I can't remember, I just say, oh, I can just, I know the hyperbolic sine, I know the hyperbolic cosine, those are easy, and I can get all the rest from there using quotient rules or power rules with a chain rule, whatever. Right? These derivative rules play nicely with, with all the other derivative rules. So if I had something like y equals x times the hyperbolic sine of 3x squared, and I wanted, for whatever reason, to know what the derivative of that is, well then, this is a product, so I need the first one times the derivative of the second. Well, the second is the hyperbolic sine of something, so the derivative would be the hyperbolic cosine of that something, but then times the derivative of the inside. That's the chain rule. So 6x. So that was the first times the derivative of the second. Now I need the second times the derivative of the first. Well, the derivative of the first is just 1. So I've got this. Right? So I had x times this function. I had a product, and then I did the product rule. Within the product rule, there was the hyperbolic sine of something, and that something wasn't just an x, so there was a chain rule that took the derivative of the inside of that and put it out here. All the rules that you had before still work. These just play nicely with those. So you should try some of these. I do still have inverse hyperbolic trig functions that I need to look at in the next video.